Good day, everyone. I am the reporter number 28 of this course code, and my topic is all about the uniform flow channel. So, open channel flow. Open channel flow characteristics. So, open channel flow is a type of fluid flow with at least one free surface subjected to the surroundings. So, the pressure is considered to be constant at the surface, and hydraulic streamlines are at the surface of fluid in open channel flow. So open channel flow is characterized by a flow not completely enclosed by solid boundaries. So free surface is subject to atmospheric pressure. Flow is not caused by external head but by the gravity component along the slope of the channel. So open channel flow occurs when there is a gravitational pull of the flow of the water. So there are types of open channels. First is the streams and rivers, the canals, sewers, tunnels, and pipelines that are not completely filled. So in the streams and rivers, an example of it is the Indus River, which are located in the Pakistan, and it is said to be one of the largest river in Asia. So next is the Tal Canal from the canals, or most commonly known as the Great Tal Canal. So Tal Canal is also located in Pakistan, which are also developed by the government. So next is the sewerage, also can be seen in the Pakistan, and as you can see, there is a sewage in that picture. So next we proceed to the hydraulic radius and the diameter. So hydraulic radius and the diameter, or hydraulic radius is often used as a mean flow depth, while the diameter is also called the equivalent pipe diameter. So what is hydraulic radius? So hydraulic radius is came from this equation. So RH for hydraulic radius is equals to the area over the perimeter wetted. So next we proceed to the hydraulic diameter. So hydraulic diameter also came from dH equals to 4A over PW. So there are also instances that there are rectangular and wide rectangular open channel. For the rectangular open channel of width W and depth D. So as we can see in the figure, it's a rectangular with the width and the depth. So RH is equals to dW over W plus 2D. And for the diameter, 4DW over W plus 2D. But for the wide rectangular open channel, W is greater than to the depth. So RH is equals to D, and the diameter is equals to 4D. So next, we proceed to the Reynolds number for open channels. So what is Reynolds number for open channels? So Reynolds number is defined as RE is equals to uh, velocity times the depth times the rho over the absolute viscosity. I think that this is a familiar equation since it was introduced to us in our hydraulic subject. But since dH is equals to 4RH, we have the equation for the diameter of the hydraulic. So next, in expressed in RH, so Reynolds number expressed in terms of radius. So by definition, steady flow is characterized by no changes in time, while the uniform flow is characterized by the water cross-section and depth remaining constant over a certain reach of the channel. So, as we can see in the figure, there are non-uniform, uniform, non-uniform, uniform flow, which indicates that at the flow AB, um, the flow accelerates, while on the CD, the flow remain uh, or established as uniform, while the D to E, the flow accelerates, and E to beyond, then it is re-established. So for any channel of given roughness, cross-section, and slope, there exists one and only one water depth, and it is called the normal depth, or the DO, at which the flow will be uniform. So next we go to the channel bed slope. So considering the following stretch of channel, so as we can see in the figure, there are the energy grade line, the hydraulic grade line, and the bottom or the bed slope. So the channel bed slope is defined as the SO equals to tan theta equals to ZB1 minus ZB2 over the length. So next we go to the water surface slope. So in water surface slope, uh, it corresponds to the hydraulic grade line, HGL, for open channel flows. So basically at this slope, it starts with the hydraulic grade line up to the bottom. So from the equation, is equals to D1 from depth D1 from the hydraulic grade line up to the bottom, which plus ZB1, and minus to the D2 minus ZB2 over the length. But since it is a uniform flow, D1 is equals to D2. So we came up to the equation that S, or the slope of the water, is equal to the slope of the bed slope. So there are, though these surfaces are parallel. So next we go to the total energy grade or total energy line. So total energy line is defined as uh, this form. So next is this, since we know that the cos theta is equals to L over Ls, we conclude that the slope or the total slope is equals to slope from the bottom then times cosine from the bottom. Then however, most open channel bed slope is small. But as for open channels, SO is equals to SW equals to the total slope. Next, we proceed to the discharge through open channel. So there are mainly two equations for the Church's formula. So the Church's formula, or which are created by the or founded by Antoine de Chessy from 1718 to 1798. So he is a French bridge and hydraulic expert. Proposed his formula in 1775. So this is the formula: V is equals to C square root of R S O. We are so familiar with this equation because it was introduced by the hydraulics. So C stands for the Chassis constant, and R for the hydraulic radius, and SO for the slope. So next is the Manning formula. So Manning's formula, or Robert Manning, an Irish engineer, proposed the following relation for the Chassis coefficient C, which is C is equals to 1 over n times R raised to 1 over 6. But according to this equation, we can write or we can derive another formula which V is equals to 1 over n, or 2/3, as 1 half, which n stands for the Manning's roughness coefficient. So next is the Bazin's formula. So Bazin formula, a French hydraulic engineer, H. Bazin, 897, proposed the following empirical formula for C. So C stands for 157.6, or over 181 plus K over square root of R, where R is hydraulic radius and K is for the Bazin constant. But take note that the values of K is will matter for what the surface of channel. Either it is smooth, concrete, smooth, earth channels in rough condition, dredged earth channel, which corresponding basins constant. And next is the Cutter's formula. So Cutter's formula, I think there are two engineers inventors that create this formula. And this is the SI stand or the international standard equation for S for the Cutter's formula. So C is equals to 23 plus 001.5, and I know it's so familiar because it is introduced also in the hydraulics, where N stands for Cutter's constant and M is for the hydraulic radius and I for the slope of the bed. And also the values of N all corresponds to the constants, and for the Mannings they are all their same instance in for the constants. So we go for the rectangular section. So for most economical section, P should be minimum. And the equation is the area is equals to base times or the b times the depth, and the perimeter is b plus 2d. For most economical section, p should be minimum. So b is equals to 2d or d is equals to b over 2. For the hydraulic radius, m or m is equals to ap, and since a is bd, and since excuse me, and since b is equals to b is equals to d 2d, so we came up with 2d squared. And for perimeter, so we know that b plus 2d and b is equals to 2d, so we came up to 2d plus 2d. So the lowest form of the equation is d over 2 for rectangular section. And next we go to the trapezoidal section. So trapezoidal section is for most economical section, p should be minimum, where the area is equals to b plus nd times the depth, and the perimeter is b plus 2d square root of n squared plus 1. And for the hydraulic radius, it's also indicate our also um, in the form of d over 2, and the theta will always be 60 for the trapezoidal section for most economical section, and b plus 2 and d over 2 or d square root of n squared plus 1. Here we go to the sample problem. For the first problem is water is flowing in a 2m wide rectangular big channel which having the Manning's coefficient n is 0.016 and the depth of 120 cm and the bed slope of 0.012. So how we estimate the flow rate? First we go to find the radius, hydraulic radius, since the hydraulic radius is not given, so we use the hydraulic radius is equals to area wetted over the perimeter wetted. So by, so for the area and the perimeter is b plus 2y, and we came up with the answer of 0.545 millimeters. And by using Manning's equation for finding the flow rate, so q is equals to 1 over n, ar 2/3 s 1/2. So we get the answer from that equation. So we get the answer 3.47. And for the next problem, this problem is a continuous flow. So suppose the widths of B1, B2, and B3 are 25, 8, and 45 meters, and the total depths are 0.4 and 2.8 and 1.1 meters. Compute the flow rate if SO is equals to 0.018 and N1, N3, and N2 are given. So now we go for the second problem. So the second problem states that suppose the widths of B1, B2, and B3 are 25, 8, and 45 respectively, and the total depths are 0.4, 2.8, and 1.1 respectively. So we have the given for the bed slope, and N3, N1, and N2 are also given. So we have we use the equation the Q is equals to 1 over N AR 2/3 SO 1/2. But since it is a continuous flow, we must first use I mean um, we must first know the flow rate of each section. But since it composed of 3 sections, we have to get each flow rate to that so that we can get the total flow rate. The Q is equals to Q1 plus Q2 plus Q3. So that's the end. So thank you for listening, and for questions and clarifications, you can contact me in my Gmail, or you can direct message me in my message. My email is dennisanselgo@gmail.com, and my FB name is Anselgo. Have a good day, everyone. That's all for my report, and I hope you have understand all the details and also the formulas that I have presented. If you have clarifications or questions, you can PM me in my messenger or email me at my Gmail. Thank you.